today we start from this example. The load AB here in this figure is supported to the 200 Newton force. Determine the reactions at the bolt and the socket joint at the point A, and the tension in the cables BD and BE. The collar at C is fixed to the load. Okay, so we can draw the free body diagram first. We have one object, and we have four support, maybe three support at the point A, and we use the bolt and socket joint. So in the point A, we have the three direction reactions. And at the BE, we have the two reaction extension force, and we have one force at the point C. So the free body diagram like this. And we can use the vector analysis, so do a Cartesian vector form. So FA, let's see FA at here, and in three direction, x-axis and y-axis and z-axis, we have the AX force, AY force, and the AZ force. So in Cartesian vector form, we use the AXI plus AYJ plus the AK. So this is the Cartesian vector form. So same concept used in the tension force TE and TD. So TE parallel x-axis, so use the TEI, and TD parallel y-axis, so use the TDJ. And the force is at here. The force is equal to 200 Newton, and the direction is negative. So we use a negative 200 K Newton because force parallel x-axis. Then we can do the summation F equals to 0 to calculate the equilibrium. So we use the every force summary together is equal to 0. So we have the I part combined together and the J part combined together and the K part combined together. Then we also can use the summation Fx equal to 0, summation Fy equal to 0, and summation Fz equal to 0. The mean is I part is equal to 0, and J part equal to 0, and K part equal to 0. So we can very easy to calculate use equation 3. We can get the AZ is equal to 200 Newton, and we can get the relationship between AY and TD, AX and TD. And then we can use the moment equilibrium. So we calculate the summation moment point A is equal to 0. And in vector analysis, we can use the position vector cross the force vector, and we can get the moment. So if you want to, if we set the moment point at the point A, we don't care these three forces because these three forces at the moment point. So only consider this force and these two forces. Let the point A get the moment. So we can use the position vector RC cross the F, and the position vector AB, we call it RB, then cross the TE and the TD. So we can use this equation. The summary every moment is equal to 0. And okay, so we know the position vector RC is equal to 0.5 RB. Okay, so we can just change a little thing inside, then calculate everyone, use the position vector cross the force, use the vector form, use the Cartesian vector form. Then we can get the I part, J part, and the K part equal to 0, and do again summation mx equals to 0, summation my equals to 0, and summation ma equals to 0. Then we can get these three equations. So we can easy to calculate the TD and the TE. Okay. So you have when you have the TD and the TE, then we can get the AX and AY answer. So the answer like this list. The next example, the bent rod in this figure is supported at A by a journal bearing, at the point D by a bolt and a socket joint, and at the point B by means of a cable BC. Using only one equilibrium equation, obtain a direct solution for the tension in cable BC. The bearing at point A is capable of exerting force components only in the Z and the Y directions, since it is properly aligned on the shaft. In other words, no couple moment are required at this support. Okay, so in this example, in this object, we don't have the moment, and at the point A, we have two direction actions, and at the point B, we have a one tension reaction. At the point D, we use a ball and a socket joint, so we have a three direction reactions. Okay, so this is the free body diagram, and we also in this equation, in this question, we only can use the one equilibrium equation to solve the tension force at BC. So now we just set the one moment axis. Then if you set the one moment axis at AD, then we don't care about this force, and this three force. Just care this force and this force. These two forces will let this moment axis get the moment. Okay, so we can set the moment axis at this line. Okay, so when we calculate the moment, because this force and this force apply on this object at this line, so I think the moment point, if the moment point at the point B, okay, the moment is equal to 0. But if you want to change the moment point from the point D to the DA, you can use this consequence. I think maybe 2 weeks ago we have this course about this part. So if you want to calculate the okay, we have the one moment, couple moment here. Okay, we have a couple moment here, and this moment we can use this. If you want to calculate this direction moment, we can use the this position vector and dot this moment. Okay, so we can easy to get the moment and y. So we can calculate the position vector first. Okay, so from D to A, okay, this is the vector or unit vector. use the unit vector, then dot these two force cross, not these two force, these two position vector cross the force. So when you calculate the weight force, that this line of the moment, we can use the position vector RE cross the W. So you can see that this. When you calculate this force, we can use the position vector RB cross the force TB. So like this, and use the unit vector dot this moment is equals to 0. So this is a Cartesian vector form, and also we calculate the I part, J part, K part combined together. Then in this part, okay, then we can get the TP answer like this. So I think the concept is same, then it's very easy to calculate. And just if you set the good moment axis or good moment point, you can very easy to find every unknown force answer. And then you also can use the, like we set the moment point at the point B, then we also can use this equation to calculate. We don't use the Cartesian vector form, also can take the answer. Okay, so we just try to calculate the other example. The uniform load AB has a mass of 40 kilogram. Determine the force in the cable when the rod is in the position shown like this. Okay, so this is the smooth color at point A. So we have the one object here, and we have three support, one at here, and the second, and the third. So in point A, we have the perpendicular reaction, and at the point B, we have the perpendicular reaction, and from B to C, we have the tension reaction. Okay, so we draw a free body diagram, and this object have no mass, so we have the loading force here. So we draw a free body diagram first. Minus TBC equals to 0. So the FA is equal to TBC. And we can do a summation F right? So FE so and we can set the moment point. If we set the moment point at this part, we only consider these two forces, let the moment at the point B, so Euler's dimension B is equal to the weight times the moment arm. The moment arm here, I think is the 1.5 meter. This degree is 60. Okay, so use 1.5 meter cosine. Cosine 60 degree. And minus, okay, because the point at here and we regarding the right hand row, so this force we can get the positive moment, and this force we can get the negative moment. Okay, so this is positive, and the FA is negative moment. So use the FA times the moment arm. Then this equation is equal to 0. So we can get the FA answer and the TBC answer. So the answer is maybe like this. If this is wrong, let me know. I will calculate again. And this equation, next example, determine the distance d. So we want to calculate the distance d for the placement of the length load p. For the equilibrium of the smooth bar in the position angle theta, show like this figure, neglect the weight of the bar. So we have the one object and we have two support, one at here and one at here, and these two support only perpendicular reaction. And we have the one force at here. So we can draw a free body diagram first. Okay, so we can use the moment, summation moment O is equal to 0, then we can very easy to calculate. So we set the moment point at here, and we do a summation moment O is equal to 0. So we don't care the FA, and we can use the P and the FB and calculate this moment and compare these two is equal to 0. So we use the minus P because regarding the right row, this P let this point get the negative moment. So use this P times the sine theta. This is the moment arm because the dP will divide it into d sine theta. So use this use this then times the moment on D, and you can get the moment. Use FB. FB also like this concentrate. We use second equals to 0. And then we also can use the summation Fy equal to 0. So the P and the speed P cosine theta. So P cosine equal to the P. And we can get the FB is equal to cosine theta. So use this result, put it into this. So we can get the B is equal to cosine theta triple. Next example, a boy stands out at the end of the diving board, which is supported by two springs A and B, each having a stiffness of K equal to 15 kilonewton per meter. In the position show the board is horizontal. If the boy has a mass of 40 kg, determine the angle of the tilt which the board makes with the horizontal after he jumps off. Okay, so we can negate the weight of the board and assume it is rigid. Okay, so now when the boy stands here, the board is horizontal. So when the boy jump, the board will tilt or maybe from this to this, and from this to this. Okay, so this is very difficult to concentrate, and we can draw a free body diagram first. And this spring, now the length is same, so length it is L. When the boy jump, I think the board maybe like this. If the boy jump, the board maybe like this. So we need to calculate the theta. Okay, so you can see the spring, the spring is the length, I think maybe it's 10, and at a point A, the spring maybe better compression. Okay, so if you want to, if the boy stand at here, the spring A is 10, is 10. So the reaction force maybe like this direction. Okay, so in the point B spring, when the boy stand at here, then the spring will compression. So we can put the reaction force this direction. Okay, so when you know this concept, then we can very easy to calculate the answer. Then we do the moment, we set the moment point at the point A first. So we set the moment point at here. So we do a summation. Moment A is equal to 0. So the weight times the moment on 4 plus we call this is B, and this is F, okay. We also can put the moment point at point T. And when they do a summation, moment P is equal to 0. So So we have this FB and FA force, FB and FA force. Then we can use these two force and stiffness to calculate the original length of the spring, of the A spring and the B spring, and we can then we know this part and this part, and we can calculate the triangle. We know spring B length minus the spring A length, then we can get this part. And we have these two spring distance 1 meter. So we can use these two side, then calculate the seat. Okay, so use FA is SA times the K. Okay, so SA, so the SA is equal to 1, we also can use FD equal to SD times K, and SD is 1, 6 by 15 equal to okay, so okay, so LA plus the SA equal to, now we know the distance is, the length is L, and use LB minus SD is equal to L. So we can get LA equal to L minus so we use these two, LA, LB. LB is the length is less than spring A, so we use LB minus LA is equal to these two. So we have this answer here. And we can use the tension. The center is equal to 10.377 degree. This is simple. The beam is subjected to the two concentrate load, assuming that the foundation exerts a linearly varying load distribution on its bottom, determine the load in intensities W1 and W2 for equilibrium in terms of the accelerometers shown like this. So we have the one object in this beam on the ground. Then we have the two force and these intensities force. Diagram first. Okay, so we can divide into this loading. Use the one part in the triangle part, and in this upper part we use the W1 times the L. The L is the total distance. L is the total distance, and in this force, center of the gravity is 0.5 L. And this triangle, we also have the force. The force is W2 minus W1. Okay, so the total force is just this times the L, then times the 0.5. And this center of the gravity, I think is here. Okay, so this is center of gravity in a triangle. Maybe I think is the D divided by 3. Okay, so divided by 3 here. So this is the L divided by 3, and so this part is the L divided by 6. Okay, so when we know this, we can set the moment point at the point A. So the moment point is a point A. So solution V equals to 0. P force. Of course, only y direction force, so we can use the summation F1 equals to 0. select it here. Okay, we have a 10 minute break.